Okay, so today will be Jorge's talk. Everybody, Jorge about the Dicke model. Very good. You can go on.
Perfectly, thank you. Let me put the presentation form. Can you see my screen? Yes.
Yeah.
Very good.
And
Okay, so thank you guys. Well, I'm Jorge. I'm a postdoc of Lea, and I'm going to talk about the Dicke system. It was a model that I explored in my PhD degree a lot of years ago. And I will tell you about this tutorial just to explain some things about this Hamiltonian, this system, and especially some semiclassical techniques to get the Lyapunov exponent. And well, the outline of my presentation is this one. I will introduce the Dicke model. I will tell you about the quantum system. Then I will connect the classical limit of this model. And the second part is just to explore and keep this frame from the classical analysis or the classical dynamics that I will explore using especially the Lyapunov exponent as a chaos quantifier of this system. And then I will use this Lyapunov exponent, especially in the Dicke model. And the last part is the homework. Now, if you have any question or comments, please let me know and I will check. About the Dicke model, this guy is Robert Dicke, that he proposed around of this year in this paper. I don't know if you see my, okay. Did you see my screen?
They see everything.
Oh.
The people here may have trouble, but I think we saw your mouse.
Oh, then let me see, because I want to project only my screen, yeah? Or did you see everything? Because it's split,
yeah, everybody's doing yes. Alexandre is doing.
Okay, very good. Sorry. And the system was proposed around of this year in this paper. And this system basically explained an optical cavity that is represented by this picture, which interacts. This optical cavity is made with photons that interacts with N2 level atoms. And the Hamiltonian that, after a lot of calculations and simplifications, the Hamiltonian is this one that basically consists on two sectors in this system. By one part, the photons on the cavity, and the other part is the N2 level atoms. That originally, well, we can think that is a many body problem, but actually it's not, because the dynamics or all the behavior around of these N2 level atoms is a collective behavior on these N2 level atoms. I mean, the system basically is a two-body problem, yeah? Which in this Hamiltonian, the first term is the photonic part that corresponds of the photons, basically. The second part is the atomic part that involves all the nature of the two N2 level atoms and the interaction of in the system between the photons and the atoms, yeah? And about these parameters and these operators, A and A dagger are the annihilation and creation operators. J Z and J plus minus are the pseudo-spin operators. This quantity N is the number of the two-level atoms in the system. Omega and omega 0 are basically the frequencies or energy in the gaps of the atoms and the atom parts respectively. Gamma plays the role of the coupling that at the same time is the more important control parameter in our system, because the other two basically are fixed in this kind of studies. And the other one, this gamma C, is a critical parameter, which is important because basically this parameter divides the system into regimes that I will explain later. but it's important because basically from this parameter, we can understand an important feature of this Hamiltonian that is a quantum phase transition.
Okay, Jorge, can I just say something, especially to Jackson? Because we just talked about this today, spin systems. So just for him to be sure that he's following. What he's saying, this JZ that Jorge said, is a sum of all the sigma z's. So he has, just as we said, many two levels. Each two level is one, but he's seeing as if all of them are coupled, like these guys coupled with this guy, right?
Yeah.
So then instead of putting this sum, he just used this thing. So instead of seeing each one as a little spin, he's seeing it as a big
one.
spin.
Yeah.
And it's interacting now. Instead of thinking about the interactions among them, he's thinking about the interaction of this big thing with some photons. Okay.
Yeah, exactly. Well, Leah explained so good this part of the atoms, and well, in this slide I present some part of the history around of this system. It's a simpler model basically because, as I told you, this is basically a two-body system. The system is not integrable. I mean that it's important because we can split in the Hilbert space sense. It was studied by the spectroscopy properties. And well, something that is important for us in this kind of studies is the quantum phase transition feature, and also the chaos properties so relevant for us because, well, we explored basically this behavior a lot in many papers. And in this sense, Tobias Brandes in this paper proposed that this behavior around of the quantum phase transition is totally related, and maybe it's an explanation of the chaotic behavior. And he explored this phrase in this paper. By the experimental side, it was done in QED systems for n in 3, and also the quantum phase transition was observed in the Bose-Einstein condensates. That is so nice because it's not only theory, it's an experimental system, and it implies also that is so useful in quantum technologies using some properties of this Hamiltonian or this model. And some years ago, I studied just with Leah this quantity that we call OTOC, that is a fancy quantity that we use a lot on these papers. And we determine this exponential growth on this quantity. And recently, a colleague from Mexico prepared a physical review article, and also it's in archive, and it's basically it's a resume of a lot of work in previous papers with this group made in Mexico. Sorry. Now, in this slide, I present basically the abstract that present Emery Brandes in the previous paper that I show. Used to say, oh, this is important because chaos and quantum phase transition are related. And here in this paper, they use this lambda as a control the parameter. In this resonance case, and the control critical parameter is this one, 0.5, and this is the n that can be explained in terms of this J, that is a relevant property or relevant quantity, that is an scalar, that basically is the measure of the number of atoms in the system. And here, this guy plots the expected value of the JC operator that is called the atomic inversion, and also the expected value of the photons numbers. And as we see, the red lines are quantum calculations, and the black one, this black one line, is the classical limit. That in this sense, the classical limit is when the number of particles goes to infinity. Yeah, sometimes it's called the thermodynamic limit. And as we can see, this black line around of this critical point is how can I say?
An abrupt change.
Yes, it makes this abrupt
Abrupt.
change. Yes, this discontinuity is in this control parameter, and it is that we call the quantum phase transition, just because we don't preserve the continuity in this kind of observable, and is around of this value. Yeah.
So then let's repeat, like for the undergrads, like, so what Jorge is saying, below this lambda, the system has some properties. Above this number, different properties. No? So we call below the lambda one phase and above lambda different phase. So quantum phase transition, right?
Yes, exactly.
And
then,
Jorge, this is expected for the ground state, isn't it?
Yes, this calculation is for the ground state, as Curro said. Yes. And then they explore just the other states, the excited states in the system, using the level spacing studies for different sizes in the system. And also they change the control parameter with a small value, the critical value, and maybe something that is big in one sense. And the black lines is the level spacings. The blue and the red curves represent respectively the Wigner and the Poisson sorry, distributions. And as we can see, when we use the a small control parameter, the distribution follows the Poisson distribution. And when we increase the control parameter, is more like a Wigner. It means that it's in a chaotic regime. And when we have this small parameter in the coupling, is more like the Poisson, that it means regular behavior. By this reason, these people say, oh, the critical parameter marks a quantum phase transition that is related directly with the chaotic behavior. Yeah, but actually it's not, because depends of which regime of the spectrum did you say. I mean, sometimes maybe if you see the first levels in the system in the chaotic regime that they show, maybe the spectrum shows something that is regular. Or maybe if you are below the critical parameter in this plot, maybe the chaotic behavior happens but in excited states. It's not a global result. But we proved this kind of results in previous in publications that we did after that.
Can you explain to the Vesh, I don't know if already knows, and Jackson, what is Wigner and what is Poisson? We see it again. You already said, but just because you said regular, chaotic, if you can just, but Edson had also talked about.
Yes, Edson talked
just
about.
Repeating, no? So, okay, so Poisson and Wigner is analysis that Jorge, these guys did for quantum, no, for the levels.
Yes.
Right? And this tells you whether the system in the classical system is chaotic or not. No? So that's what he's saying. Poisson, they associate with regular in the classical. Wigner in the quantum, you associate with chaos in the classical. No? Okay.
Yeah. And so just going to the classical Hamiltonian, for that we use the coherent states. Why coherent states? Is because coherent states are, well, I think that is because are the more classical quantum states, because minimize the uncertainty principle of Heisenberg, and in this sense is the more classical quantum states, and are useful just to project the system in the cloud in the classical sense. And here I present the Glauber that is useful just to project the atomic part, sorry, the photonic part. I mean that this is the coherent states that act for the photons, and the other part, the SU2 coherent states, are from the coherent states that works in the atomic part. Yeah, we can split these coefficients in the Fock basis and in the pseudo-spin basis. Yeah, it is useful if we want build from the quantum domain the coherent states. But in our calculation, we will use explicitly these coherent states because we can describe this alpha and this zeta using complex numbers. These complex numbers are related directly with position and momentum in the classical sense and in the classical phase space, where this Q is the position and this P is the momentum for the, for the photonic part, the photons. And in the atomic part, we can project with this zeta that I call in lattice, sorry, with this other zeta in Greek. But it depends of the theta and phi variables that also are canonical variables. And with this in mind, we can write, the classical Hamiltonian after this expectation value. And the classical Hamiltonian is this one with four components, four coordinates. Yeah, I don't know if someone has any question.
Yeah, people should ask if you.
I have a question.
Yeah.
What is theta and phi?
Theta and phi are related with the variables in the Bloch sphere, because well, it's something that maybe I forget explain, but the pseudo-spin variables, it works in the Bloch sphere, and theta and phi are the angulars.
I think and so you got it right, but it's the big spin here.
Sure, no.
And then we have the angles there.
Yeah. Now, I will talk about some properties in this system. One property about the symmetries in this Hamiltonian is that
One quick question. The size of the system now is infinity.
This other thing, we divide this quantity over J.
Yeah, and you take the limit J
The
to
dependency
infinity.
of the J, of the dimension of the system, yes.
Okay.
Well, symmetries. One symmetry that has this Hamiltonian is the change of sign with P. If we exchange the sign with P, it's the same Hamiltonian. I mean, this is a symmetry. Other symmetry that has this Hamiltonian is the change of phi, this phi. If we sum or add this P, it's like a phases in the classical sense. And it's the same if you change this Q for minus Q. It's other invariance property that has this Hamiltonian. And I will show in a visual sense, selecting P in 0. If we select P in 0, we can get the Q variable in terms of the Jz, phi, and the energy that I will call epsilon, the classical energy. And we will, in future slides, I will call Q1 and Q2, which is okay. And I select, for example, these parameters to gamma, omega, and P, just to project in these variables, U and B, the energy share of this quantity. And as we can see, we see different colors that corresponds, for example, the red one corresponds with the yellow, are symmetric, and the blue with the green, because are the same, because as I tell you, if we exchange, for example, this phi is the same quantity put in the other side, positive or negative, etc.
So Jorge, just can you go slowly because now, so what we did was we put from those four variables, you put P0.
Yes.
So now you can do a projection in 3 dimensions, right?
Yes, exactly.
Okay. And then you have Q, okay, U is a mix of theta and phi, and V also theta and phi. Okay.
Yes, I fixed the energy, exactly. Just to project in a 3-dimensional plot, the energy share, exactly.
And again, can you tell me again the colors? Because,
Yes.
how you define these colors?
Yeah, it's because I write this Q, this projection of Q, and I split we can say the parities in the system, and the blue is connected with the green.
Okay, so it's to show the symmetry, right?
Yes,
So this is an
yes.
illustration of the symmetry. Fine, I
Yes.
understand. Okay, thank you.
I have a question.
Question.
Yes.
Yes. So here you said if P equals to 0 and then Q is equals to something, and how did you get this? Like
Sure.
the left part.
Yes. Yeah. Basically, is this plot of this function, the Q plus minus, that depends of two variables. Yes. JC, phi, and epsilon. Yes.
Yes.
And if we plot this quantity in 3 dimensions, is this globe, these two globes.
Jorge, maybe what Alexis is asking is, how did you write this equation for Q, right?
Oh, yeah.
It came from the Hamiltonian.
Yes, exactly. It becomes from the Hamiltonian because the classical Hamiltonian is the energy.
So he puts a value of the energy,
Yes,
correct?
with epsilon,
So
exactly.
he has now a constant,
Yes.
and then that equation, he isolated the Q from that equation.
Yes, I solved the roots for Q because it's a quadratic expression for Q in the Hamiltonian. And I get the information of Q using the general formula of how is it? Second order polynomials in Q. And I solved.
But you see, Alex, that in this equation for the Q, there is a little epsilon that showed up in the equation below in the Q plus and Q minus.
Yes.
So this epsilon is the energy that Jorge put on the left side there, where the Hamiltonian was, he put this epsilon. And then he isolated the Q, right?
Oh, so he used the small energy, I mean small e, to replace the Hamiltonian and then solve the
Yes,
equation.
exactly.
Okay,
Exactly.
thank you.
But
You're
but
welcome.
this isoenergy surfaces. So these are
Yes.
surfaces with the
Yes.
same energy. Doesn't need to
Yes.
be large or small. You just fix a value for the energy and you solve your equation. And
Yes.
what you're plotting is energy surfaces. Okay.
Exactly. It's the
So
energy
that means
surface.
that all the points in these surfaces have the same energy.
Exactly.
They are
All-
related by some transformations.
Yes. Yes. Now, something about the integrable limits on this Hamilton.
Edwin.
Edwin has a question. Yep.
Yeah, so it may happen that your Q can be also complex, right?
No, Q is only real. All the classical variables are real numbers. Alpha is complex, but Q, P, phi, and theta are reals.
Okay, because the first term inside the square root is positive, epsilon. So epsilon. Okay.
Yeah. You say that maybe this root it could be complex. The answer is yes, but from in the Hamiltonian sense, it's only for real numbers.
Thank you.
So something about the integrable limits. One integrable limit is when the coupling is 0. It means that we have a constant in the dynamics that is easy if we think that the classical Hamiltonian looks like an oscillator with other one. If we cancel the coupling is two oscillators and two oscillators are integrable. Yeah. If we cancel the dependency of omega 0, P disappear, and it implies that Q prime is 0. I mean that Q is constant, is other quantity conserved. It's an integrable system. And also if omega 0 is 0, the first term disappear, and it's the same history, is so similar to the previous one. We can change the frame of phi doing a rotation. And with this rotation, we can rewrite the Hamiltonian in terms of a new Jx, And in this sense, Gx don't depends of the fib x and its other integrable limit. Yeah, it's other conserved quantity. Now, something about the classical dynamics. Well, first I will change the variables just to write the previous Hamiltonian maybe in an easier frame or a structure.
More friendly notation.
A friendly notation, because it's useful just to represent the system like two oscillators with this nonlinear interaction. Yeah. In this sense, we will pass this system in a mathematical thing that is a dynamical system, which this x represents the phase space variables with these differential equations that are given by the Hamilton equations. Yes, and the Hamilton equations are, the equations that will represent the dynamics in any dynamical system, and are this one. And this is the Hamilton equation on the Dicke model. And also we can represent the Hamiltonian in angular momentum variables. If someone wants to explore the properties that are in the torus, etc., but we usually work in the previous structure only with P and Q's variables, but it's fine. Sometimes it's useful just to reproduce the Hamiltonian in these angular momentum variables. Yes. So now I will explore a little bit and explain something about the energy and the dependency of the coupling parameter. And as Lea said, when we have this critical parameter, the system has one kind of properties before of this critical value that we call the normal phase. And after this value, one quantity that is visible in this plot is the minimum of the energy. The minimal energy changes because before of this quantity, the minimal energy is -1. But after that, the minimal energy changes and makes a superradiant phase. That is another regime of the system in this control parameter. Yeah, and these dashed lines represent ESQPTs that I will tell you more with this animation. Now, here I fix, for example, the coupling parameter in 2, and I show with this red line. And here I will show how the energy shell change when we increase the energy in this system, fixing the coupling parameter and the other parameters with P in 0.
Jorge, so we are going along the red line, yeah?
Yes, we are
So we
along of
start
this.
at the bottom and we are going up, and that's how we are seeing the surface there, yeah?
Yes, exactly.
Very nice.
And for example, when the animation starts, we are in the two sectors, and suddenly these two touch. And this, when they touch in this point, this is the first SQPT. And the second SQPT is when the energy shells split.
Very nice.
This is the second SQPT. This is the meaning, or this is the one way to represent the SQPT behavior in the classical sense. Is how what is the abrupt change in the surface in the classical regime. Yeah. Now I present these energy shades projected only in the atomic part in these capital letters in the phase space. When I define, for example, these special energies, 2 below of the critical energy of the first SQPT, and 1 above, the green one. And we can see the contour lines of these 2 energies, yes? When we are below of the first SQPT, we have to, it's like a double well in this projection. And if we increase the energy of this shell, we have this hyperbolic point. That is, this is the point when the energy shells touch Yes,
Mhm. Yeah, you're waiting
and
to
looks
see.
like this in this three-dimensional plot. Yeah, the green, the red one, and the orange one. Yeah, it's small. It's okay. Now,
Can I ask you something? So
Yeah.
what we were talking before, none. So the states below that energy of the ESQPT, all of the lines are degenerate, right? We have you have pairs of degenerates,
Yes.
left and right. Okay.
yes, yes,
So
after
the
generate.
same thing as the care and all the others.
Okay, just a quick question. When you have two split surfaces, no, here in this, you have two surfaces for green and red. That means that there are doublets of
Sorry,
generated energy levels.
sorry.
Can you
Can you
repeat?
repeat?
Yes,
Now.
in the yellow and the red,
Can
you have two
Yeah.
Wait a
sections.
second, Curro.
Yeah. Ooh, this is me. I sound possessed. Is it better now? Now it's better? You can hear me?
Yes, yes. I
Yes.
think they close the microphone to
Okay.
avoid the wow, 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 wow.
Okay, I can ask later. Don't worry.
Oh, no, it's
Now,
okay.
the problem
Okay.
was here.
Ah, okay. No, just a quick question. I don't want to stop you. Here you have two sections in yellow. That means that you have like two wells in your classical limit, and you have two degenerate or quasi-degenerate states. Okay.
Yeah.
I'm curious because in the previous slide, if you go to the previous slide, Jorge, and the previous to this, here, you have in the second ESQPT, you have again, when you have high energy, this split again into two. Does this mean that you have again doublets of the generated energy levels? You see now that splits into two surfaces, and you are at high energy.
Yeah, I understand your question, Curro. So,
Maybe we can leave it for the end, and maybe for the end I will be gone, but Jamil will be here, and this is something that interests us and also Miguel. But just if you have a quick answer, it's okay. If not, you can leave it for the end. I don't want to stop your seminar.
okay, maybe late, but it's okay.
Okay, perfect.
Yeah, can you hear me now?
Yes.
Very good. Okay, we continue. Oh, okay. Now I will tell you about the classical dynamics. For this, I will tell you about the Lyapunov exponent and the explanation of this quantity. Basically, the Lyapunov exponent is a measure of separation in one sense. When we start with an orbit and a small perturbation of this one, yes? For the beginning, they are so close, maybe with a distance delta dx. And when we evolve any kind of orbit, they will separate with the variation of this one. And this distance could be exponential, yeah? And basically the ratio of this exponent is called lambda, that is the Lyapunov exponent. If this quantity of this separation increase exponentially, the system is called chaotic. Or if it's maybe a polynomial is not chaotic, it's only regular, yeah? It is true, but it's not totally true, because the distance, if you have, for example, an integrable, a Hamiltonian system, you know, the system is bounded. And obviously the distance, they never
keep growing.
Exactly. They never keep grow
Indefinitely.
indefinitively because the system is bounded. Yeah. In this sense, sometimes it's useful just to prepare or just to make measure about this distance using the tangent space. But it's one method just to get the information about this Lyapunov exponent. And in this sense, people use this quantity as a method used to quantify the chaos in dynamical systems. Yes. And other quantity that is important is the inverse of this Lyapunov exponent that is called the Lyapunov time, that sometimes is related like a measure of uncertainty when you have a chaotic system, because the idea is just when you have a chaotic system, when you evolve classical orbits, after one time, the chaoticity can spread around of the classical phase space with a kind of randomness. Yes, in this sense, is a measure of time just to say, oh, in this regime of time, your system is predictable. Yeah. So
Predictable.
predictable. Yeah. But after this
After
time,
that, you
no.
lose.
Yes, exactly. So now I will explain something about the variational equations just to get the Lyapunov exponent using this matrix that is called the fundamental matrix or the monodromy matrix. If you have, for example, any d-dimensional system, the fundamental matrix is a d-squared dimensional matrix, and we need solve both at the same time. By one hand, the dynamical equations, and by the other hand, the fundamental matrix or the monodromy dynamics on this quantity with these differential equations and with these initial conditions. The initial conditions for the dynamical system and the initial conditions for the monodromy matrix. That is sometimes is called the variational method. Yes. And with this, we can get access, for example, at this variational distance using this product between a small distance or difference from the initial condition and the monodromy matrix evolved in time. Yeah. And the Lyapunov exponent is get when you multiply this monodromy matrix with the transpose matrix, you take the norm of this quantity and divide over 2 times t in the limit when the time is or goes to infinity. And this is the way to get the Lyapunov exponent. In the case of the Dicke system, this is they are the differential equations that I call F, and this quantity is the Jacobian. Yes, that I will use to reproduce the monodromy matrix and get the solution of this quantity.
Can you go back one slide just for
Sure.
me to write down this equation? Okay, so
Mhm.
the monodromy, it will come from the Jacobian.
Yes,
Okay, fine, I wrote it.
yes, exactly. The monodromy matrix satisfies that the derivative of this quantity is the Jacobian times the monodromy.
Okay, and this monodromy at time 0, you just put an identity.
Yes,
That's how we started.
yes,
Okay.
exactly. And the explanation about why is the identity is because in the initial state, the variation and your original initial condition is the same, and you don't have a
No
variation. Exactly. Well, and it's okay. Okay. And after that, we use this scenario just to put the dynamical equation of the Dicke system using the Jacobian and the dynamical equations. And for this kind of system, we have that the dimension is 4. I mean that the total dimension to solve numerically is 20. And you need to solve 20 differential equations at the same time with these initial conditions that I wrote before. And for this kind of system, we need use any kind of numerical methods like Runge-Kutta, etc.
But I don't understand, why 20? Where do they come from?
Yeah, because
Because
we-
you have to put one on the other.
no, because we have 4 equations
Right.
for the Hamilton-Jacobi
Right.
equations, and 16 equations that are given by the monodromy from the because it's a matrix.
Fine.
Yeah, and we need to solve all of them, all of this coupled dynamical system.
So Jorge,
with
when you
numerical
solve
methods.
this, you have the solution for Q, the time evolution for Q, P, capital P, and then this other phi.
And the monodromy,
phi.
no?
And the
Because
monodromy.
it's important.
The monodromy, because
But-
it's a matrix that is the square dimensional.
Yeah, and then, but you, the monodromy, you truly need it just to compute the lambda.
To
Yes,
compute
it's just to
Lyapunov,
it's
right.
exactly, it's just to compute the Lyapunov, because just to get the Lyapunov, we need the information in time for this monodromy matrix.
And this is the module. This is what you have there.
Yes,
This-
this is the norm.
Okay, of phi that has, and this phi has 20
16.
d squared dimensions. Okay, so it has
Yes.
16.
Yes, it's 16 plus the 4th equation of the from the
Yeah.
Hamilton equations are the 20.
Yeah. Yeah.
So just to illustrate this solution, well, I plot the orbit using only the Hamilton equations with these parameters, gamma into gamma critical. I preserve the resonance in the system with 1 and with this energy. And I introduce this initial condition. And this Q1 or Q2 are solved using the expression that Elik asked before. Yeah. And for example, with this initial condition, the orbit looks like this, the complete orbit in the 2 projections, in the P and Q, the small, and P and Q capitals. Okay. And the other one is with this orbit, and we say, okay, maybe they are not so different, but the left, the first 2 images are regular, and the other one are chaos, have chaos. How we can know that this is chaotic or not? For that, we use the Lyapunov exponent. And sometimes it's useful if you use only some special points in your orbit. For example, from the previous orbit, this one, I select only the points that are satisfied, for example, P0, the P is small. And in this projection, I have now a set of points that cross this surface with P0. And this is the point that is called the Poincare section. Yeah. And it looks like a closed orbit. And when we have a chaotic behavior, these kind of orbits are broken because the idea is just to break the torus in the dynamical system. And this is the classical behavior of any chaotic initial condition.
Very nice. But you can understand, so this is for the same initial condition that you had before? No, now.
No, are for 2 different initial conditions, but at the same time with the same energy.
So the next plot is for this energy.
Yes, exactly. It's respectively each case. And here I plot the 2 different distances that we can plot. In the first part, in this one, I plot the real distance in the phase space, the distance explicitly between a small condition close to the original initial condition, and they follow the same behavior. So this distance is the geometrical distance, the distance that we know in geometry differential. I don't know. Differential geometry? No.
What is the
Analytical geometry? Well, the classical distance. And the black line is the distance that has, sorry? Well, so the classical distance, and this is the red one. No, is the black one. The black one, and the red one is the distance provided by the variance using the method that I showed before. For this method, this is the distance.
Ah, now I understand. So these are two different distances.
Yes.
One is the one that is coming from the monodromy and all that.
Yes, the red one is from the monodromy, and the black one is the real distance in the classical sense, the distance in the four-dimensional space. Yes, and they grow small, and it's so small. Yeah. Now, we plot the same distance, but for the initial condition that is chaotic, and as we see, in an period of time, they are so similar. But after, for example, 100 units or something like that, the geometrical distance converges to something because it never increased so much because the energy shell is bounded. But the variational distance increase in time. And this slope, basically the slope of this quantity is the Lyapunov exponent.
But so then if you would look at for short times up to 100, you could still get to that slope looking at the
Yes.
classical. Okay.
Yes, by this,
But it's not so good, probably. Well, it's
Yes,
just
but-
a small interval.
yes, but in this sense, some people use other methods
Mhm.
because at the same time, the definition is the time goes to infinity, but at the same time, the initial difference between the perturbation and your original orbit is close to zero.
Mhm.
And if you reduce the distance from the beginning, it's other way to calculate the Lyapunov exponent. Yeah. Using only the natural distance in the geometrical sense. And we can plot in time this quantity, for example. This lambda is provided by the variational method.
Mhm.
And this quantity is relevant when the time is bigger, yeah? Goes to infinity, and this quantity is small. And this one, it goes to 0.051, that it means chaos. Numerically, we use this cut just to define, if this quantity is small, that 0.003 is regular. If it's bigger, it's chaotic.
Maybe a comment.
Yeah,
The-
say loud.
The difference because the normal distance is calculated in the phase space.
Yes,
But the variational is in the tangent space.
it's in the tangent space.
Can you repeat what he said? So people-
Yes. The thing is that
The blank.
the black one is in the distance in the phase space, and the red one is in the tangent space. It's using the variational method
Right.
that works in the tangent space. And for example, we can plot in many different initial conditions just to show, we can say something about the percentage of chaos using, for example, the Lyapunov exponent as a quantifier, using different energies. For example, in this sense, we use an lower energy for this system, and maybe we have a big percentage of regularity. Maybe we can see in the blue part in this phase space. Jonathan.
Go on, Jonathan.
Jorge, should I speak in Spanish or in English?
English.
Just kidding, just
People
kidding.
who don't know anything about Spanish.
Just kidding. Yeah, okay. No, okay. No, it's interesting. Well, let me ask you a question because I'm confused with the tangent space because you have the phase space and one learns that the divergence of the trajectories are in the phase space. And there is where from where you extract the Lyapunov exponent. No, what is physically this tangent space, and how are you confident of these results? I mean, the behavior of this exponent in the tangent space is just because it gives you this exponential increasing with time. I don't know if my question is clear.
Yeah. Sorry. Sorry. Yes, I understand your question.
Remix.
I don't know so much about the physical sense or the physical scenario of the tangent space. I understand that is because in the tangent space is an unbounded system. In this sense, we can increase this quantity indefinitely. It's working. It's fine.
Indefinite.
Yeah. Yeah, I think that is one reason. Other thing that is the first approximation of the dynamical system, because it's the linear approximation of the dynamical system, because born from the Jacobian system. And maybe this is an argument just to say something about the physical thing. But I don't know so much about.
Do you want to say anything?
Maybe Miguel has.
It means because the tangent space can information about the asymptotic dynamics of it.
So Miguel is saying that the tangent space gives information, asymptotic information about the phase space.
Exactly. And geometrical, you
Yeah,
can evolve vectors in the tangent space.
yeah.
You
Okay.
evolve vectors in the tangent space.
You evolve vectors in the tangent space.
Then how much the vector is increase or decrease.
How much the vector is getting extended,
Yes, stretch it.
stretch it, okay.
Is the Lyapunov exponent. That is.
That gives us information about the Lyapunov exponent.
Yeah.
Yeah, because I was thinking, okay, thank you. But I was thinking, yeah, just I want to understand, because this tangent space is like a trick in order to, I know, to extend the space and to continue, I mean, for the Lyapunov exponent to continue growing with time. And so, but how do you know that this is the the physical increasing of the Lyapunov exponent with time? Now, maybe you contrast this with the phase space, as you say, the Poincare sections, and this is consistent with the Poincare section, no? But how do you know that this is the correct numerical value of the Lyapunov exponent? Not only the correct behavior, I mean, the exponential increasing, but the correct numerical value of the Lyapunov exponent. I don't know if my question again is clear.
I haven't had control of this yet. At short time they match. That's the only thing that I said.
You can evolve a time.
A big time, yeah.
Big time.
Yes.
Sure.
I don't know.
I
think that depends of which kind of system, because maybe for example here I plot the dynamics around of by 500 units of time, but maybe for other system 500 units of time is so small time. I think that depends of your system, especially in the scale units, I guess. But the definition is by the definition is used to when the time goes to infinity, and numerically infinity is something that we caught in the numerical calculations.
It is also there exists a spectrum of Lyapunov.
Yes.
And
Yeah.
it says you calculate just one, the maximum.
Yes.
But if you calculate the spectrum, you have an n spectrum, the number of the dimension of the system, the difference. More information, the convergence.
Yeah.
Miguel is talking about the spectrum, the Lyapunov spectrum, Jonathan.
Yeah, because maybe in one previous slide, this one, I use only the norm of this product, because I'm interested only in the bigger one. But as Miguel said, in general we have vectors that can spread the dynamics or reduce the dynamics in different directions in the phase space, and this kind of vectors or directions are explained by the spectrum of the Lyapunov exponent. That is, and this information born from this product. I use only the norm because I'm interested only in the bigger one. But in general, we have four dimensions. At the same time, we have four directions that are explained by the spectrum in the Lyapunov exponent.
If this is for the distance, in the phase space, you just can calculate the maximum Lyapunov. But with the rational method, you can calculate all the Lyapunov expected.
Okay.
Yeah.
And yeah, for example, other thing is some properties is that this is a dynamical system that preserves the energy. In this sense, if we calculate the spectrum preserves some properties from the Liouville theory. And from this sense, the spectrum will has four Lyapunov the four quantities, and two of them are zero, because one thing is because the energy is conserved, and by conservation, the sum of the Lyapunov exponents needs to be zero because the Liouville theory, and it means that the Lyapunov exponent is one quantity that is positive and the other quantity is negative. In this sense, the maximum Lyapunov exponent here in this case is the same that the positive Lyapunov exponent in the spectrum, because the other one is zero and the other one is negative and the other one is zero. So this is some properties of the Lyapunov spectrum in dynamical systems.
Okay, you can continue, Jorge. Just was curiosity, so
Yeah.
thank you.
You're welcome. So maybe, for example, here we can increase the energy of the system, and as we can see, the Poincare section shows this spread in this kind of points, and this is one way to detect chaos visually, but quantitatively we can check the Lyapunov exponent as, and here we see a small island of stability. And also, if we increase more the energy, basically all the phase space is chaos, and the Lyapunov exponent basically show the same thing. Yeah. And here we can explore, for example, more things. If we fix, for example, the control parameter for different energies, we can create a map just to say, in this regime, for example, here for small couplings, the system looks like a regular system. But as I told you, before of the critical parameter, we can check that in this regime are chaos. That is not shown by the result of Brandes.
So they were not looking at the whole spectrum.
Exactly. And here, if we increase the control parameter by 2 or 3, the first energies, in the classical sense, of course, are regular. But after that, we have chaos. And also it's visible if you put, for example, the Hilbert space that corresponds on this regime in the quantum sense. In this part, we can see Poisson. But if we are in this regime, we will see Wigner.
Okay, but right at the critical point, it's true that all levels, almost starting from the ground state, already indicates chaos, right? Right when gamma is equal to critical. Right there, yes, where your mouse is. So there is it looks like almost all the levels starting from the ground would be chaotic, but this is a particularity of that choice of parameters, so omega equals to omega 0, right?
Yes.
You could also change that at the critical point, right?
Yes, we can change omega 0, and yes, as
and then we wouldn't start with chaos right at the ground state, perhaps, right?
Yes. Now, well, the next part is the homework. For that, let me explain this code just to get the Lyapunov. This is in Mathematica, and well, let me see again the homework.
Yeah, tell us what the homework is.
Because the homework is two things. The first part is just to get the classical Hamiltonian from the quantum using these properties. We know that the J plus, J minus is this linear combination of GX and GY.
You can.
Oh,
Sorry.
yeah, but about that.
I don't know why.
That's strange.
I don't know,
Sometimes
maybe.
that is what,
I don't know what.
if not, I can show to them. Someone.
Oh, yeah, you can see?
Okay, yes, yeah, everybody can see. I can see on mine and they can see.
Yes, and here the idea is use these properties, J plus, J minus, and this is expected values for these coherent states for the SU2 algebra or the pseudo-spin algebra, and the other two for the coherent states in the Glauber sense with these classical variables just to get the classical Hamiltonian. This is the first part. And the other part is improved the code that I will explain or I will share with you in the language that you prefer, Python, Julia, etc.
Anything Jorge can do.
Yeah. Yes, and so I don't know if I have time there or
Yeah,
it's okay.
you can just conclude.
Okay. This is the code used to get the classical Lyapunov exponent. We write the Hamiltonian. We define this function. This is the way to define something in Mathematica. And after we define the parameters that we select, omega, omega zero, the energy, the coupling, the critical coupling, the time that we will evolve the system. For example, here, my time is 5,000, yeah?
Then you
Yeah.
the equations, right?
Here I write one way to check the Hamilton equations in a symbolical sense. I define this ratio f just to say, okay, in this case f is 2.
Uh-huh.
And now I will write the initial conditions. For example, this initial condition implies P1 in 0. And let me change the initial condition, this one, by other one. Okay. Okay, why this initial condition is because in my presentation, I want to reproduce something that I showed before. Oops. Let me see. Okay, this one. Here, P is 0. Q is the solution of the analytical structure of Q, sorry. Capital P is 0, and the capital Q is this quantity, yeah? And I solve symbolically this this quantity Q with this command that is solved from the Hamiltonian, just to get the information of Q, my initial condition. And I use Q1, yes, because we have two roots just to get Q. Yeah, I show in the previous slide. Now we can verify that all is fine. I run the first part in the code, and this is the initial condition, and I calculate the Hamiltonian using the initial condition just to prove that the energy that I wrote is fine. That is -4, -1.4, and the coupling is this one. Yeah. Okay. Now the next part is how to solve the dynamical equations of the system. Yeah. The first part is write the dynamical system. I mean the Hamilton equations that I call F. Yeah, because I call this guy F. So F, it contains all the information of the four equations, yes, the Hamilton equations in my F. Now, I mean, in this part, I write P prime, Q prime, capital P prime, etc., and so on. I define my initial conditions in this part. Now, I define the Jacobian matrix by hand using this thing. With this in mind, I take the derivatives of any list by the variables that we can use, and I define the Jacobian. And after I use now the Jacobian that I define using my Hamilton equations on the variables Q, P, etc. All the other variables. Now I will create the monodromy matrix. For this, my first 4 variables are the Hamilton equations. Now, the next 16 equations are the monodromy variables. Yeah, are 16. And the dynamics around of the monodromy matrix is the product between the Jacobian with the monodromy matrix.
And the
And-
issue is identity.
Exactly, and the initial condition for this equations for the monodromy matrix is the identity matrix. Yes, I put the initial conditions with this in this way. Is one way to wrote. Oh, this is the 0, 0, 1, 1. This is the identity basically. And in Mathematica, it's possible use this solve that is one command used to get the solutions, numerically solutions of differential equations. Of what? Okay. In this part, I join all the Hamilton equations with the respective initial conditions, with the variational part in the variation, the monodromy, and the initial conditions. That is basically the identity. For which variables? For all of them that are from 1 to 20, because are 20 differential equations. In what regime of time? From 0 to t, that is 5,000. And I specify the method. I use explicit Runge-Kutta of order 8. Yes. Sometimes in some package like Python, etc., people use order 4, and it's fine. It depends of the resolution that you want numerically. Yeah. And here I say that, okay, this is a command used to say, okay, improve the numerical method using steps of 10 to 9, a lot of steps in this window of time, and improve this numerical agreement in Mathematica. Yeah, because usually the numerical resolution is 15. Yeah, but I improve 30. And at the same time, I include this command just to say, okay, but this is nice because the system is Hamiltonian, and we can verify that the efficiency of your method, if you take the difference between the original energy, that is in this case is minus 1.4, to the Hamiltonian evaluated every time, because this is a problem in the numerical methods. The numerical methods includes numerical noise. In this sense, we lose information when you evolve a lot of time in the evolution of the time, and it is a way just to verify the efficiency in your numerical solution. And I say, okay, my numerical error, for example, is 10 to minus 6. If this difference is small that this quantity, it's fine, and my numerical solution is acceptable at this time. If not, well, you could at the time that is valid this error, that is fine. And here I calculate the monodromy because it's given by the 5, 6, 7 to 20 variables both at time t. It is my infinite time in one sense.
Which is not 5,000 anymore, it became T-max, right?
Yes, it's T-max. In the best way, if the numerical, if the numerical solution is fine, maybe it's the same,
Maybe it will.
but depends. Exactly. And after, well, sorry, in this part, I defined twice this thing. And it's okay. Now I have the calculation of the Lyapunov exponent. That is the monodromy matrix times the transpose of this matrix. And I take the norm of this quantity, the logarithm, and 1/2t. And this is the way to calculate the Lyapunov exponent.
Very nice. So what do we have to improve over that?
Sorry?
You said that we have to improve something. It
Um,
looks very
no.
good already.
No. The idea is try to reproduce
To
this code
reproduce, okay.
in the package that you prefer, in the language that you prefer.
Excellent.
And
Okay.
here, for example, I have the solution give us that the Lyapunov is 0.00. If I mean that is regular.
Right.
And for example, for the other initial condition, that is also with P0, sorry.
The other one is chaotic.
Yes. You do the other
Let's
route.
take this code. We do it right now. No, it is pretty good. Okay.
And this is positive, yeah?
And we can also look at the orbit.
Yes, we can check the orbit. For example, if we take the table of these variables, we can define, okay, I will save the data and all this information for my orbit, and we can plot, for example, the solution in the Q versus P or something like that in time.
This takes some time. No, it's
Yeah.
solved.
This is the evolution, but this is chaotic and looks regular, but it's chaotic.
Yeah, we have to look at the Poincaré now.
Yes, it is
Okay,
okay.
okay.
And that's all.
That's it. Very good. I liked it very much.
I see
There are
something.
some people asking, okay, no, that's fine. So I'm going to stop recording because this is already too big.